Okay. Well, thanks everyone. Really excited to kick this off. Fringe Inspection user panel. So appreciate you guys joining and really excited to share some insights from the users of Fringe Inspection and how they've been using this technology to hit their goals and to really advance additive manufacturing. So I'm going to go over a little bit of overview of what we're doing at Phase3D, and then I'll let the panelists introduce themselves, and then we have about 5 or 6 questions to go over from there. All right, so this is kind of the motivation behind what we do at Phase3D. We believe additive manufacturing has the potential to really be a game changer in the manufacturing space. And we know companies like Elementum, Alloy, researchers like CCAM are using this technology to make high quality, high performance, highly critical end use parts. But we feel that the rest of the industry as a whole is held back by the lack of real-time quality inspection, certification, a born qualified method of additive manufacturing. And that's what we're focused on solving at Phase3D. We see that the primary AM challenge today is lack of confidence, high scrap rates, but we see a potential through real-time quality inspection to get to lights out production, parts being printed on demand with a high quality guarantee. Our product that we've developed is called Fringe Inspection. It's a in situ inspection technology that uses structured light to measure the printing process. We take a structured light scan of the powder layer, we take a structured light scan of the melted layer, and we measure anomalies in real time during the printing process. Within Fringe Inspection, there are 2 softwares, part of the software suite. There's Fringe Operator, which serves as a digital twin. It shows your part as it's being printed. It shows anomalies that are forming, quantifies them, characterizes them, and lets users get a real-time indication of part quality. We've also released Fringe Qualification, which is a dashboard that helps users keep track of anomalies, observe trends, and keep printing conformance in prescribed thresholds to keep that qualification and the high confidence in part quality. All right, so I'm going to pass it off to Andrew to kick things off for the user panel.
Great. Thank you very much. I'm Andrew Holliday. I'm the Applications Engineering Manager here at Phase3D. And first off, just want to kick it off with each one of our panelists introducing themselves. So we can start off with Adam, if you want to go ahead.
Yeah, thanks, Andrew. So I'm Adam Polizzi. I'm the Engineering Manager at Elementum 3D. I've been at Elementum for a little over 8 years or so. My educational background, I have a metallurgical materials engineering degree from Colorado School of Mines, as well as a project management professional certification through PMI. Initially at Elementum, I was the lead aluminums engineer, focusing on aluminum alloys and aluminum matrix composite development, and then earned my PMP and moved into the engineering management position thereafter. So these days I work mostly on project management, but with all material sets and technologies that we have at Elementum. And then I've also done a lot of development in our QMS process and procedures for design development.
Great. Thank you very much. And Callum.
Hi, everyone. I'm Callum Churchman. I'm here from Alloys, and I am the manager for process engineering in our core technologies business unit. My background is that I've been working at Alloy for about 3 years now, since I graduated from the University of Cambridge with a master's degree in natural sciences, specializing in materials. So yeah, great to meet you all.
Great. Thanks, Callum. And last but certainly not least, I'll pass it over to Kyle.
All right. Thanks, Andrew. I'm Kyle Snyder. I have a background in material science and engineering, so it seems like that's a theme for the panel here. I've been at CCAM for about 7 years, and we do a lot of, it's a research organization. We focus a lot on in-situ monitoring in different processes. So I lead a lot of our additive efforts in powder bed and also DED, but powder bed is definitely a lot more advanced with sensors and data processing and analytics. So yeah, we do a lot of work with setting up custom sensor systems, yeah, I've been very happy so far with getting some data from Phase3D. So we have it set up on a couple of machines in Virginia now.
Great, thank you very much. And with that, we'll go to our first question and just kind of go around the horn here. The first is, can you share what you enjoy about using Fringe Inspection? I'll pass it off to Adam first, or Kyle. Go for it.
I'll go ahead and start. I'm still unmuted here, so yeah, I can actually give a good example. Just this morning, we were running a build, and everything looks fine if you look at the top layer just in the door of the machine. But I went over to the Phase3D panel, just did a quick filter on the anomaly table, and saw that there was a couple of layers consecutively that had a pretty large anomaly detected. And so I was able to just kind of quickly scroll to those layers, see what issue was occurring. Basically, we had a pretty large flat overhang area, caused a lot of warping, some recoater contact. And so not only did we see the hopping and streaking, but we saw that some of that streaking was dragging material into more sensitive parts with thin walls. And so now we're going to be able to pull this build out and target some of that inspection and some of the NDT that we would typically do on these parts.
Yeah, I could definitely take it from there and add to Kyle's review there. That was, yeah, thanks, Kyle. Yeah, one thing that we've been really enjoying at Elementum is the easy communication between our printer techs, printer operators, and engineering, and vice versa. It's a common language. You can see the pictures, and then even in review, having the three different images from each layer, the recoat, the exposure, and then the back travel of the recoater, with the optical images. You can correlate where you might see defects, where they might be occurring in the recoating and exposure process. So it's definitely helped out a lot with being able to communicate these things, and yeah, kind of deciding what the next steps are in investigation. Whether we cancel a part, we keep going. Whether we do NDT testing or something like that. Yeah, definitely, it's been a pleasure to work with in that way. It's brought the two departments much closer together as well.
I think from my point of view, the thing I've enjoyed the most is the insight it gives you into the process that it's really difficult to achieve by other means, and particularly the insight into the varying layer thickness you get throughout the build, depending on whether you've got overbuilding, the fact that your powder is consolidating and leading to a greater layer thickness, and even if you had it in your head, you were laying down 50 microns of powder each layer. That's not necessarily the case, and not the case for the entire build. So just the way it opens the door to think about the process in a way that you hadn't before is what I've enjoyed most about it.
Great, thank you very much. And now, Kyle, you touched on this point pretty briefly, but can y'all share any specific defects or anomalies that Fringe Inspection helped you detect? Especially those that would have gone unnoticed or completely missed or been found too late? And how has this changed your build decision making, whether they fail or not, or even your rework rate?
Yeah, sure. And I should start it by saying a lot of the work we do is assessing sensor systems. So we really want the defects and the anomalies present. So we're really kind of balancing that with our builds. But I mentioned we see a lot of the recoater hopping and streaking, which is indicating, a part is probably warped through the powder layer to cause that contact. So you may have some thermal challenges going on as well. And so those, I think the detection, we've seen it detect the major events there. Also with short feeding, that's a very obvious, to see within the data. And so those are, I think, the more obvious anomalies that we see. Some of the things that I know you guys are working on more detection capability, but I mentioned with the recoater streaking, there was some material being dragged through the powder bed. And so we could see that in some cases it stops on the next part, maybe it gets pushed through on the next layer. And so being able to see where that material that was removed, if it kind of joins another part, sometimes it'll get melted into that part or melted to the side of that part. And so we're starting to see, easily trace those issues as well. And sorry, not to kind of jump at it again, but we also have a project ongoing right now with partner R3 Digital Sciences, where they've built a tool to try to take the in-situ sensor data and provide feedback so you can update your build plan. So basically, if you're overheating, it'll tell you to reduce power. And so we actually were able to implement the Phase3D system into that machine learning program as well. And so we're getting things like how much is the part warping through the powder layer. And so we're still trying to define the best metric there to capture. But I think really where this is hitting is how openly accessible the data was, all the image files for us to be able to kind of access ourselves and be able to pull those into different programs. So we can basically combine that with other sensor data as well.
So from our point of view, we did kind of some of our own validation activities on it, and a really big thing for us, and particularly the components that we print for consumer electronics, is trying to push the limits of what sort of specification limits you can put on the geometry in your part, and being able to detect recoater damage very precisely and say whether it's going to push your geometry out of spec and whether you could get away with it or whether it's gone too far is really it is something that we were really impressed by and could definitely provide a lot of value for us.
Yeah, absolutely, I agree. Yeah, and then with additive, I mean, pretty much all things additive are new until the application process and development is complete and is going into production. And Elementum, we specialize in not just the materials development, but also the application development for customer design parts, and being able to section some of the highly complex portions of the parts and everything. We can see where parts are either deforming, having recoater contact, knowing blade wear, recoater wear, like you were saying, Callum. It's really helpful to be able to I guess if a parameter set or an orientation isn't working whatsoever, we can cancel that part, and we know it before it either destroys the build or we get to the end and we spent an extra 4 hours in that build building that small little part of the DOE, and shorten our build times and even expedite some of the development processes as well.
Great, thank you. Now, how has integrating Fringe Inspection into your process affected your qualification timeline, R&D confidence, or even your QA next steps?
So for Elementum, we haven't quite integrated with our QMS yet. We're still learning and getting the data and everything. But this printer is involved in a MMPDS type CD basis level qualification for one of our aluminum matrix composites. That printer is one of five printers on the project, and it's definitely given us confidence in those builds. They're all complete now. And thank goodness we saw consistency and everything with everything, but we were able to verify that throughout, considering these were 4-day builds each. It's nice to not get to the end and realize the issues at the end. We were able to have confidence and sleep better at night, let's say, as these builds were continued over the course of their timeline.
Yeah, so we've been kind of developing our understanding of the fringe projection system in a project that we are undertaking. It's a UK government-funded project focused on the development of a digital qualification platform, and it's generally focused on how do we incorporate these sorts of digital and in-process monitoring measurements that you can take during the build that can help build confidence in qualification. So it's kind of going hand in hand in that development effort for us. But in this project, we are developing and qualifying an aerospace component, which takes a week to build in itself. So as Adam was saying, it's so useful to have technology that allows you to monitor, and if you're running a build for a week, if you can stop it after day 2, it saves you a lot of time if it does go wrong. And I think also just getting the understanding of parameter optimization. We have to do so much, which is basically using the process engineer's instinct on what do we think will improve the quality of the material that we're printing, and just being able to have an extra piece of information which informs us as to what's actually going on with the powder bed, and is there anything that we'd assumed was happening that actually is happening, is super invaluable, because a lot of the novelty of LPBF and the issues with optimizing it are that we aren't able to look close enough at it. So just giving process engineers another way of observing the process and evaluating why you might be getting certain defects in your development builds is super invaluable for developing a robust process that's qualifiable.
Yeah, and so some of the stuff that we're doing, assessing different sensor systems, it's all trying to lead to, quality assurance, quality control. Like what data can we use to inform us on quality? And so I think, that this is one of the first systems that we were assessing, and this is the one that we've progressed the furthest. So to actually get it installed on our system, and one that we work with at a Navy facility as well. And again, their focus is quality assurance right now. And so, we're looking at what can we get from Phase3D that we don't get from other systems, and that's the height maps, and really what does that mean for the build? You can detect if a part's warping, or if you have some hops or streaks, but that doesn't always lead to those are anomalies that don't always lead to defects. And so we're trying to find that more kind of actionable information within the data. And so one approach we're trying to take is really trying to pull out like a flatness metric for the entire build. And so I think this is somewhere where you can get confidence in the quality of your parts, where if you can look on average across your entire build, say you maintain 95% flatness, versus other builds in a different orientation. Maybe you have some rough layers that only have an 80% flatness. So kind of a vague metric term right there, but if you get what I'm saying, the information is there. We're not getting this from other sensors like optical or thermal cameras. And so I think, in my opinion, there's kind of 2 key things to get from process monitoring. That's capturing your thermal history, your thermal signature, and then also capturing your distortion. And if we tie that back to some of the pre-process steps like simulation, those are 2 of your key outputs. And so I think this is kind of building a robust data set across the workflow, where you can get outputs in your pre-process, compare that during your process, and then have that information in the post. And so having those metrics that align to other information in your workflow, I think is key for quality assurance.
Great, thanks all. Now, kind of as an extension to that question, how do you plan on using these unit-based measurement data from Fringe Inspection to actually help you align with qualification standards, such as AMS 7032 or even internal QA gates?
I think in-process monitoring like this, it's the kind of start of what's going to have to be a paradigm shift in the way that we do qualification. And from our engagement with aerospace customers, there's a bit of an assumption that if you lock down your process, nothing will ever go wrong because you've controlled everything, and then we can just press play on the build and it will go over and over again. And I think what this opens the door to is direct measurements that you're taking that you can't really deny. It's like taking a gas flow measurement. You're measuring the height of your powder bed. You can't argue with that and we kind of know what that means. And it gives you a way of making sure that, of providing an extra data set to say, look, all of this, our build should be fine given that this data comes out okay from the fringe inspection. So that's kind of one way that it improves it. But the other way is in R&D, the generation of robust parameters and being able to get that better understanding of the process. Because if we're ever going to regularly get AM components into aerospace, which have very stringent qualification requirements, we need to make sure that we're printing material that has high enough materials allowables for it to be to be worth the kind of risk on the novel processing strategy. So I think it paves the way to having that more robust process through the better understanding and the adjustment of your build file to make it as good as possible, to make sure that the material that we're producing through laser powder bed fusion is performing well enough that we're exceeding the traditional limits for the material allowables that we're working with.
Yeah, utilizing that height map and those discrete measurements, you can really start seeing those build anomalies or possible defects come up. And based on previous data and everything, you can assess whether you're going to see a depreciation of properties or a failed build or something like that. And once that's all taken into account during these qualification stages, it really helps with the ensuring that the parts and the operational qualifications are coming as expected. Basically, it's another data point, and it's good data.
So, yeah, I think in regards to the unit-based measurement, when you're talking about qualification, especially to a big entity like the Navy, Air Force, something where quality is very critical, having an actual unit value is very important. A lot of these, what I call process intelligence tools, sensors, software, whatever it might be, there's a lot of black box AI machine learning that takes place. And so I think there's a lot of value to go down that avenue. But I also think at the end of the day, if you're trying to qualify parts or process, you need to have some real measurements. Again, being able to connect that to the different stages of your workflow. I think a quick example is some parts we've printed that are kind of a thin, a small cross-section part that are taller. They can kind of act as like a bit of a lever. So when they get hit by the recoater, they'll fling powder in one direction and leave a crater behind. And that's something that we've seen for years with optical cameras, but we never knew the magnitude. And so we could see that would fill in maybe after a couple of layers of recoating. But until now, we can actually track that progress. And maybe in some cases, you disturb the powdered bed so much that you can't correct it in a reasonable amount of time. And you get short feeding effects behind that crater. And so this is an opportunity to, kind of take that and fail faster, essentially be able to stop that build or maybe stop some of those parts before they become affected there.
Great, thanks. Now we have one more question that's pretty forward-looking, and I'm interested to hear your responses on each one of this. But personally, how do you see in situ inspection evolving in the next few years? And what do you see systems like fringe inspection doing, and what do you think their role will be, and why?
I think a big one's going to be machine integration and smart processing. Whether it detects a short feed, which is a pretty simple and straightforward function, and then it automatically recodes before exposure, or it even can detect high and low points after exposure, and allow for even parameter adjustments on the fly, small parameter adjustments to try to help with the any sort of complexities in the part that may benefit from a change in parameters on the fly, something like that. But yeah, no, this is like dreams out in the future, and it'd be really cool if we can get there and you see inklings of it. Some OEMs do have the short feed imaging and can recoat prior to. Being able to do this with discrete measurements, unit-based measurements, it only makes it more precise and a faster correction.
I agree with Adam and the fact that the 3D printing industry needs to move towards these abilities to correct on the fly so that it's robust enough to kind of achieve everything that's been promised with 3D printing. Because as any of us who've worked with a laser powder bed fusion and have tried to run the same build file, even on different machines in the same room, there's so much that can go wrong and so much variability. So this stuff is frankly necessary for laser powder bed fusion to be as widely applicable, because it's a really expensive way of making things currently, and so the material properties have to be way better for it to be worth making your components out of it, or it needs to allow you geometry that you couldn't achieve by other means. And it also needs to be, you need to be able to send a build file and manufacture it somewhere completely different. And you're going to need in-process monitoring to achieve that robustness. You can't just tie it all up in a robust build file. And something that Kyle said really resonated with me, which is the fact that when you're looking at your build process, there are two things that are going on. You've got the thermal behavior. Everything's thermal. You're melting material and solidifying it. And then also the shape of the material, of the part that you're printing and the bed that you're printing onto. So those are fundamentally the things that we need to focus on. And I really want to see less of the over data heavy ML analyze, trying to pick out defects as they form. I think in-process monitoring that directly measures physical things like the shape of the powder bed, the temperature of your part, no one's going to argue with the fact that they affect the quality of your part, and actually inform a better understanding of the process, rather than trying to get a machine learning model to run and understand the process that we can't even optimize ourselves fully yet. So that's kind of where I see this going, which is why I really love the unit-based measurement. There's never going to be a state of laser powder bed fusion where it doesn't matter that you have got a lump in your powder bed. So that's kind of where I see the industry going.
Nice. Yeah, I think in line with Adam, very, very future looking. I think our big goal here is a born qualified part. That might take 5 years, it might take 10 years, but I think it's feasible. And I think a couple of things are needed. One is strong correlation to NDT. We need to know if your sensor shows this signal, that this is what it corresponds to in terms of quality, microstructure, properties, whatever it might be. And that's going to depend on the application and whose part it is. But then I think the other key thing is integration to the system. And so, and I'll say, Callum, you hit on this earlier too, that everyone just thinks, oh, you have qualified parameters in a machine, so just go ahead and run it and everything's going to be fine. And it's absolutely not the case. And especially a lot of that development was done on cubes or simple blocks, simple geometries. And so you get some aerospace parts in there. Navy is usually not too complex, so we have it easy. But yeah, once you put some overhangs in, once you have some thin walls, some unique features, a lot of that standard process window kind of goes out. And so you need the ability to monitor your process and be able to make changes. And I think that's probably the biggest barrier is more acceptance of institute data tied to quality, and then being able to use that to modify your process. And so I think with the big kind of DoD players right now, they are hesitant to make those types of changes. It's already a big lift for them to open their qualification to basically print parts instead of cast, forge, machine. And so, trying to take this new process that's that they're skittish about and say, we're going to vary the parameters as we're building is a huge red flag to them. But I think that's the disconnect And I think we could use the in situ data to kind of prove that you need to be able to make these changes in real time.
I think that's an excellent point. I think breaking down that barrier of it always frustrates me that because you've got control over the laser, people start worrying about making minute changes to or changes on a microscopic level to the power that the laser's delivering, as if that makes it a kind of repeatable or reliable process by just like doggedly sticking with the same parameters for your entire build file. And it's giving people the confidence that you can break down those barriers to have dynamic parameters that will actually produce more robust material at the end. I think that's a really great point.
Yeah, absolutely. Change that paradigm. There's definitely that paradigm in the industry that needs to change a little bit. But we also need the capability to do it consistently and effectively as well. And right now we don't, and tools like this can definitely help drive that.
Yeah, I mean, I completely agree from my standpoint. I also think you may or may not agree, but a lot of the additive industry, especially in laser powder bed fusion, has been heavily driven by this kind of tribal knowledge of what is good, what is bad, even down to, I think we all go through the rite of passage of doing your first scratch recoat. And it's such a personal thing of, is this good, is this bad? There's no real way to really show that. And in your opinion, is kind of this move towards calibratable and repeatable measurement data removing some of that tribal knowledge and moving it towards a more repeatable process?
Yes, I totally agree. That sorry, could not get off.
No, you're good.
But yes, I think that's a big part of it is it's a lot of this like institutional knowledge. A lot of the big OEMs like to keep things locked down, and I mean it's a good business strategy, but it really limits research and development, and it keeps things siloed. And so I think being able to have a more standard data set that it's not just a low resolution optical image, but more useful in situ data, having that more publicly available, and also having alignment there where you're looking at the same data, the same resolution, same quality, you're looking at the same types of features. I think that can really boost that, kind of get that knowledge and understanding to a critical mass outside of those major institutions.
Right. And I have one question also from David who's attending is, how much of the fringe inspection data or in situ data are you truly using in real time versus how much is due to, after the build analysis? And where do you see the split or value occurring?
Elementum, we've been doing some of the post-build data review with a lot of our mechanical data, and just trying to correlate anything that went wrong. Unfortunately, we haven't had a lot of development projects on that machine since we've had the equipment. So we haven't had a lot of that. So the correlation data is pretty minimal at the moment. So basically, right now we're focusing a lot on the during processing, during the build data, watching the screen, reviewing the height maps from overnight, all that, just to increase the efficiency of our builds. Basically, making sure if something failed on day 2, we don't need to build 7 days of it. So so most of it's during the build.
Right.
I think again, we haven't used it extensively for kind of manufacturing runs where we would probably want to be cancelling builds that had gone wrong, but I see the kind of calculus breaking down in favor of the looking at it during the build and being able to cancel things, because that's where the real value comes from, is being able to stop your build before it finishes. Because we tend to do a kind of non-destructive testing, like fairly quick non-destructive testing on a lot of our parts anyway, but really saving that time and not completing builds that we already know are not good, or suppressing parts that we know are going to damage other parts, is really valuable. And then in the long term, the kind of feedback loop is going to be the most important thing. So that's inherently in situ.
So yeah, we do a little bit of both at CCAM. Still a little bit fresh with the system, and we're learning how to use that effectively. But I gave the example of this morning. You know, we were still the build still going to at this moment. We were able to see that we had some issues, but the build was able to correct itself. We probably have 2 defective parts, but we're able to track that now with the Phase3D data. In terms of the post-processing, that's really where we're focusing more of our development and use of the data. So we have several other sensors on our system, and we also have several different data analytics models that we've been developing. Some of that's through commercial routes like Adiguru and Oak Ridge, the Peregrine tool. But we're really in that step of trying to combine the different sensing modalities and process that through some data analytics tool. So right now, I think the key is combining the thermal data. So we have a long wave infrared and a near infrared camera. And I think that we're still building that new model up now. But I think as we talked, getting thermal signature and distortion are 2 of the key I think anomaly indicators in the process. And so combining that data, I think it just strengthens the detection on both sides and gives you a lot more confidence too.
And with regards to multimodality sensing, is there a certain sweet spot that each of you see within the additive process? I know we've all kind of been burned in the past of having sensors that don't really give much value. In terms of combining data streams, is there kind of a happy medium that you think would work well towards qualification and production?
Yeah, hopefully we can start to figure that out at CCAM. Right now we're kind of at the cast a big net and kind of see what we catch. But yeah, like I said, thermal and distortion are the key things. But yeah, I think yeah, I guess I don't want to keep harping on the same thing, but I think that's the key thing to combine. The big challenge is data capacity, data retention, and so that's really what we see. With the handful of sensors, I think we generate a couple terabytes of data on like a 1 or 2 day build, and so. What do you do with all that? That's why we have the data analytics models that we're building, because it helps reduce that. And that's also why we're trying to look for something like that flatness metric I mentioned, to where you can take, say, tens of gigabytes of data and compress that down into maybe, a gigabyte or hundreds of megabytes of information. And that's something where with a lot of these DoD groups, they need to keep that information for years potentially. And so you can't ask someone to store terabytes of data over that course of time. And so I think that's an area. So we want to have enough information to have that born qualified part, but you're kind of making that balance of how much is too much and what's actually needed long term.
Yeah, I think, I mean, again, how flat is your powder bed? How hot is your part? And I think sensible, physically informed metrics that obviously correlate with defects in a way that we understand is the way to go, and not storing terabytes and terabytes of data, and not building an ML model that's going to tell you exactly where all your keyhole pores are. I think is somewhere in the middle of that spectrum is what I'd like to aim for.
Yeah, the more I thought about it, listening to Kyle and Callum there, I think it really depends on what your end goal is. Are you developing materials? Are you developing parameters? Are you doing application development? Are you doing production? We're all going to be looking at different things, because at each step there's a different focus, a different anomaly, a different defect that we're looking for. So I think having either similar to the Fringe equipment, the unit-based measurements is a phenomenal way to basically streamline the understanding of what you're looking at. I mean, you can look at a sliding color scale and everybody gets a different answer, or you can look at the measurements, and based on what you need, you might be looking at it a different place or in a different way. So I think Fringe definitely is a huge step in this process. But as far as what that sweet spot is, it depends, in my opinion.
Great. Well, I want to say a huge thank you to everybody who attended, and of course, thank you to Kyle, Callum, and Adam for being our panelists today. If you do have any additional questions about Fringe Inspection or about Phase3D, feel free to reach out to me, and of course, check out our website as well as LinkedIn. Once again, just thank you to everybody for attending today.
Thank you.
Thank you very much.
Yep. Thanks, Andrew. Niall. Thanks, everyone.
Bye.
Bye.
See you later.